Good morning, good afternoon, and good evening, everyone, depending on where in the world you're dialing in from. And welcome to today's webinar on how we benchmark cloud providers. Now, we are going to just turn on our cameras for a little bit to introduce ourselves and introduce you to some of the faces behind the brand here at Cockroach. My name is Maria. I am the Director of Demand Generation, and I'll be your host and moderator today. I am joining today from our New York City headquarters together with Nathan. And Andy's joining from our San Francisco office today. So actually, Andy, I'll let you introduce yourself first.
Great. Well, it's great to be here to talk with everybody. My name is Andy. I'm a product manager on our core team here at Cockroach Labs. And so I'm very, very excited to talk with you about this today.
Hi, and I'm Nathan. I'm a software engineer here on our core performance team. And I'm filling in for Masha Schneider, the original author of the post.
Great. And just quickly before we get started, I just wanted to go through a few of the housekeeping rules. First of all, to let you know that we are recording today's webinar. So for those of you watching the recording at a later point, great, we welcome you as well. And we will send out a follow-up email in the next 24 hours with the recording, and as well as an invitation for our next webinar, which will be on March 7th, and will be about migrating your applications from MySQL. But today, throughout the webinar, remember that you can submit your questions in the Q&A panel, and we will try to answer them live and also at the end of the webinar. So I think we're just going to turn off our cameras again and then let you guys focus on the content, and I'll just hand it back over to you, Andy, to get started.
Okay, great, Maria. Thank you very much. So we have four things that we want to talk about today in our agenda. The first is why we decided to benchmark cloud providers. The second is gotchas we encountered along the way. Third is sort of open source tools used in the report and some of the specific gotchas on those tools. And then we'll kind of wrap up with what we learned from the exercise. So it's kind of funny, the intention, we didn't set out to write the 2018 cloud report when we got started. We actually decided to start testing some of our new features and releases in the CockroachDB, the database product from Cockroach Labs that we produce. And as a part of testing these new features, we observed different performance outputs with really the exact same setup. And so this got us thinking, well, perhaps there's different components going on in the cloud. As we brought these tests to multiple different clouds to try them out, we were seeing different performance results. And so we realized that actually that there was a lot going on here that we wanted to dive in deeper in and understand better. And it's as a result of doing this analysis for ourselves and for our own product that we came to really learn a lot more about how the clouds work and how these different inputs can affect your results. And so we, as a part of that learning, decided we wanted to package it up and share it with others so that they wouldn't have to go through exactly the same steps we did. Although today we have updated our cloud report that was originally published in the end of last year to actually include those exact steps. So if you want, you can actually go to that link directly on our website, and within the 2018 cloud report, there's actually all of the exact commands that we ran to obtain our results. And so they're all using open source tools and open source products. So anybody can go out and kind of reproduce our findings as well as use the exact same tools, because one of the points we'll cover later on in the presentation is that these things change, and benchmarking the cloud is sort of a continuous process. So today we'll mostly talk about tips, gotchas, tricks, things we learned along the way, rather than showing the specific commands that we ran. But as I said, all of those specific commands are available in this guide. And so if you're interested in that, please do go ahead and download that information. So we'll begin our story here in 2017, actually, where we benchmarked GCP and AWS on a number of different sort of performance benchmarks that are important to us at Cockroach Labs. And our findings in 2017 were that GCP actually outperformed AWS. And this was kind of the mentality that we approached in 2018, is that, okay, GCP is a little bit better. We'll keep that in mind. Of course, we test continuously using GCP, AWS, Azure, DigitalOcean, and a number of other platforms. but in terms of, performance, we were kind of looking in that direction, and that was sort of our understanding of the state of the clouds as we got into 2018. But this didn't even last 1 year. And so what's interesting is that, in this chart on the right part of my screen here, it discussed TPC-C, which is a benchmarking throughput that we'll talk more about. And it shows basically that AWS was about 40% better than GCP when running TPC-C. And so the takeaway from this slide is really that the results we had in 2017 about GCP didn't even last 1 year. And this is because of the continual investment from the cloud providers and improving their machines, improving their performance, making them better and better. And so, we'll talk more about the specific finding and kind of what we learned along the way here. But I think the thing that was really interesting to us is that it really highlighted how continuous the nature of the improvements are, and therefore, if you want to pick the most performant cloud, you have to have a similar continuous benchmarking opportunity. So the cutting edge of the cloud, I think, is something that's interesting, because a lot of times we tend to think that the performance is stagnating, and I think it's interesting to see this. And so we'll talk about maybe one of the investments that AWS made that seem to suggest it might be part of the reason here. But at the very least, we know it's something that's different between when we observe the performance gains. And so we'll talk about that here a little bit later. So that's a little bit about why we decided to do this, the initial results that motivated our deeper dive into the information. But now I'm going to talk about some of the gotchas we encountered along the way that are important as you start to go through this process yourself. So the first thing I'll say is that it's really important to pick your instance type with care. There are many options on AWS and GCP that include variables like CPU, SSD versus persistent disk, storage size, and so on. And so because both AWS and GCP continually invest in these machines, there's often new versions available. And so on AWS, this can be sort of seen, we'll take the general purpose machine type, the M series here. The M4 was the previous generation. Now there's an M5 generation. And so, at first when we were looking at the machine types, we found them a little inscrutable in terms of the names on AWS, but then we start to unpack them and we actually realize that you can tell a lot by looking at just the machine type itself. So one thing that we would definitely recommend is that, if you're using a M4 type or a C4 type or anything that's not the latest generation, you almost certainly benefit from upgrading to the newer generation of AWS machine types. And oftentimes it's, AWS wants you to upgrade these as well. And so the pricing can be, incentivized to make that upgrade as well. GCP takes an interesting approach in which they don't actually change the name of the machine type. So, N1 standard 16 is something that we use pretty frequently, and it'll continue to make updates, but they chose not to change the machine type primarily because it makes you need to change your scripting, right? So if you have a script set out, now you know that it'll always kind of work because N1 standard 16 will always be the name. However, what's comprised within the N1 standard 16 can change. And so, for example, right now they have Skylake and Broadwell processor types, right? And so this is something that makes it a little harder for you to tell when something has changed on GCP, but it comes with the benefit that in terms of your scripting and other things, it's a little easier to take advantage of. I touched on this a little bit with GCP, but you need to care about the processor type, not just the named instance type. And this is because you can see variability among these. In GCP, they actually adopted the Skylake processors a bit earlier than AWS, which means they got them earlier so that people got to take advantage of that performance, but now AWS has newer models which run at a higher clock frequency. And so unfortunately, you can't just look and see like the Skylake processor. You actually have to dig in deep and understand when it was adopted and how those things change. And this makes it really a bit opaque in terms of looking at the cloud providers and understanding exactly the type of performance you're going to get based upon the naming of them. So that's why, having a process in place to benchmark is oftentimes the best way to do this, because, you can see the results firsthand, whereas, otherwise you kind of have to dive pretty deep in understanding exactly all the configuration options available. And so we tested multiple configurations of machine types on AWS and GCP. On AWS, we tested the general purpose, which are the M series. So we looked at both the M4 and the M5, because those are the two series that are sort of commonly available. M5 being the newer generation, as I mentioned earlier. We looked at the storage optimized series. So this is the i3 series. The compute optimized series, which is the C5 and C4 series. And then we also looked at both SSD and what Amazon calls EBS storage devices, which themselves contain different options. So EBS has both IO1 and GP2 option types. And these EBS types can actually include additional choices, like how many IOPS you want to provision, which itself is a big component of the pricing here. So there's a lot to unpack when you look at this, because you can look at the M5 SSD or the M5 EBS GP2 or the M5 IO1. So there's three different types that all fit in the M5 series here, which can all make differences depending upon what your workload is and kind of how it's run. We also looked at dedicated instances on AWS just to see, do you get extra performance? Is there a noisy neighbor problem? Those type of things as well. And so we tested that. Similarly on GCP, there's a little bit there's fewer sort of diverse instance types in terms of the name series, but we did look at both the processor types, the Skylake and the Broadwell on GCP. And we also looked at GCP's dedicated instance types as well. So we tested a lot of configurations on here to kind of see what the different outcomes would provide. We ended up, for the purposes of this report and the numbers that we reported on, choosing default instance types from GCP and AWS that got the best performance that we observed. So we wanted to give both clouds the opportunity to put their best foot forward here based on kind of the standard configuration that people go through. And so you can see the kind of the setup here of the comparison, and really they're pretty similar between the two. GCP has a little bit more RAM available, but otherwise very similar CPU, processor types, storage types, et cetera, here in the testing. And so we kind of wanted to make this as apples to apples as possible on the default types. It's also worth noting here that you can't actually make them exactly identical when you provision custom types here, but we chose not to do that because we wanted to kind of provide the most broadly accessible types available to different consumers. It's one thing we've thought about maybe exploring for our next test is setting them up exactly the same, but that's just one thing to keep in mind. Finally, I'll end on this. There really is no one size fits all here. It's important to test these different configuration types for your workload. And also, one thing that we won't talk too much about today, but also factors into this is price. And so it's important to know the sort of maximum performance you can get on all of the machine types. And then it's also important to know the different prices for those in order to pick the right trade-off for your organization between performance and price as you test here. So this again is another reason why it's important to have a process by which you test these different machine types to allow you to take advantage of the right trade-off for your organization. So next up, we have some of the open source tools used in the report, and I'll kick it over to Nathan to take us through that.
Thanks, Andy. So we're now going to discuss the open source tools that we used in the report. This is an important topic to go over because the hardware in the cloud is going to change over time. Cloud providers are continuously investing in their cloud infrastructure, and the results that we saw in December could be outdated in a matter of months. So we'd hope that for people to come out of this talk with a few new tools in their tool belt and an understanding what kind of measurements they should take when performing this kind of exploration in the future. When we performed this testing, we chose 4 areas to measure: 3 subsystems to micro benchmark, and 1 top-level application benchmark. The first subsystem that we measured was CPU performance. This is a pretty broad surface to benchmark, as it is affected by variables across the hardware and software stack. The variables range from processor microarchitecture and the memory hierarchy of your system, up to the hypervisor and the system kernel running on top of it. As Andy mentioned before, these characteristics are affected both by the cloud instance types that you choose and the cloud platforms that and the CPU platforms that your cloud VMs are placed onto. In fact, the characteristics can even differ across VMs on the same, that claim to use the same CPU platform. So we know that there are a lot of considerations in moving variables when benchmarking this layer of the cloud. Let's see how we decided to do it. As always, the first step to benchmarking is deciding what you want to measure and then picking the right tools to perform those measurements. In the case of CPU benchmarking, there are actually a number of metrics that we might want to look at. These range from exercising floating point operations and bit manipulations to measuring the performance of control flow patterns. So when looking for a tool to start measuring CPU performance, we started looking at the most commonly used benchmark test suites that could measure these various metrics. What we found was that Sysbench and StressNG appear to be the frontrunners in terms of their ubiquity for performance CPU benchmarking. Both are open source, both can test various aspects of CPU performance, and both provide useful reports of their findings. In the end, we decided to use StressNG for CPU benchmarking. This was primarily because it offered more stress mechanisms and provided more flexible configurations than Sysbench. Not to worry though, we will come back to Sysbench when we start looking at storage IO benchmarking. As it turns out, StressNG has an interesting backstory. It was originally intended not as a measurement tool, but as a tool simply to make a machine work hard. The idea was to thrash a system hard enough to trip hardware issues such as thermal overruns or kernel bugs. After being used in this fashion for some time, the tool's authors realized that the same stressing mechanisms could also be used to perform targeted benchmarking. These different stressor mechanisms are the key to StressNG. The tool comes packaged with a large suite of stressors, and each one exercises one or more subsystems of a computer. I've listed some examples here. The matrix stressor stresses floating point operations and a system's memory hierarchy. The semaphore stressor stresses the kernel semaphore implementation, as well as performing rapid context switching between OS threads. Finally, the branch stressor stresses a CPU's branch predictor. So we can see just how varied these stressors are in terms of the work that they perform. And after finishing this work, each stressor reports performance through a stressor-specific bogus operation per second metric. As the name implies, it's best to avoid lending too much weight to what these operations mean, other than in using them to compare across runs of the same stressor. So we see here an example of benchmarking results comparing CPU performance between two systems. This is from our cloud benchmarking report. But again, we're not intending for this talk to be a full discussion of the results we published there. You can download that from our website. Instead, I think it's useful to discuss the process that we took to perform such comparisons. In this case, we ran the same stressor on multiple systems. We were running the CPU stressor that we'll talk about later. We performed a series of trials on each for a few minutes to increase the statistical significance of the results that we saw. This gave us more confidence that we weren't measuring something else. We then compare the results of the individual trials, and more importantly, of the aggregate results averaged across all the trials. From here, we can get a feel for the relative difference between CPU performance on our two systems. And we can also learn about the stability of individual systems by observing the variance between trials. We can see here both systems are pretty stable. They don't have a lot of variance between the trials, but there is a difference across the averages. So here are some tips and gotchas we discovered while performing this testing. The first tip is that in most cases, unless you know exactly what you're looking for, the CPU and the matrix stressor from StressNG are probably the easiest ways to get insight into your system's general CPU performance. The former contains a number of operations that it sequentially walks through, like square roots and fast Fourier transforms. These are basic operations but they do a good job stressing different components of your processor. The latter provides a good mix of memory, cache, and floating point operations to stress the CPU from all angles. It does so by performing matrice multiplications, matrice additions, and matrix transpositions. The first gotcha might not come as a surprise, but it's worth repeating. BOGO ops are stressor specific. Don't go trying to compare values between multiple stressors, because the results won't make sense. And finally, the second gotcha isn't something that we ran into specifically, but it's something that users should be aware of when running stressng. If you run with root privileges, this will prevent Linux's out-of-memory killer from killing the process, which can have disastrous effects. Next, we're going to talk about network performance. Depending on your application and the demands you place on your cloud, this might not be a concern, or it might be the most important data point you look at. Of course, for us at Cockroach Labs, we're dealing with a distributed database that consistently replicates data across machines. So this is a huge deal for us. As with all network benchmarking, we're going to split the test into two chunks. In the first, we'll look at network throughput, and in the second, we'll look at network latency. And note that when we're doing this, it's important to be aware that these measurements are going to change based on the network topology that you're running. For instance, if you're measuring network latency between VMs in the same zone, you're going to get very different results than if you're measuring network latency between VMs across zones, but in the same region. So you should measure whatever topology you're interested in, but always keep in mind what your setup is. And just to clarify here, the throughput defines the amount of data that you can move from one location to another over a period of time. Meanwhile, latency defines the time it takes to send some specific piece of data from one location to another. Often we define latency in terms of the time it takes to move data from one location and back to the original location. This is called round trip latency. To measure these metrics, we use both the ubiquitous ping utility that comes pre-installed in most distributions of Linux and the more powerful netperf tool. Both tools are great open source options. And in this case, we use ping to measure network latency and netperf to measure network throughput. So let's take a look at network throughput results that we published in a report. Again, this was measured using the netperf utility. We have concrete reproduction steps of how to get these results in the report that we published. So we ran the same benchmark on multiple configurations across two different clouds. Again, we performed a series of trials on each of these for a minute. Multiple trials allowed us to gain more confidence in the results that we saw. And unlike for CPU performance, for network throughput, it's interesting to look not just at averages, but also at the full histogram, which netperf gives us. Here we can see that not only does AWS have a higher average network throughput, but they also have a much smaller spread. These are both desirable properties. Now let's take a look at an example report about network latency. Again, we ran the same benchmark on multiple systems, and we performed a series of trials on each for a minute to get more confidence in the results. For network latency, it's again interesting to look at a histogram of these results. Here we see that not only does AWS have lower average latency between VMs in the same zone than GCP, but they also have a smaller spread between these results. These are important both to know what your application can expect on average from network latency, but also on the effects they can have on the tail ends of the operations. Here are some tips and gotchas we discovered while performing network benchmarking. The first, which we talked about before, is to always remain conscious of your network topology. Network benchmarking, by its very nature, is completely dependent on the network between your hosts. So understanding the details of how the network is working is critical to drawing any real conclusions. Likewise, when running these tests, ensuring that your VMs are communicating via their internal IP addresses is critical. By default, cloud providers will assign each VM an internal IP address that is unique to the VPC network that they give you. Benchmarking network performance within this VPC will give you the most relevant metrics to what your application will actually observe. The next tip is to be careful when choosing a network protocol that you're going to perform benchmarking with. iPerf supports the use of both UDP and TCP network protocols. Pick the right protocol for your use case, because that's important to the results that you'll get. It can have dramatic effects on both throughput and latency. For instance, UDP throughput is not impacted by network latency, but TCP is. Finally, we did run into one major gotcha when performing latency tests using ping. It turns out that ping's default periodicity is 1 second, which can measure CPU coming out of various C states. Using an interval flag to run ping with a higher frequency, we can prevent the machine from switching power modes and skewing benchmark results. So this is something to be aware of whenever performing these types of tests. That you want to avoid all external background noise and focus in on exactly what you want to see. Our third and final micro benchmarking area is storage I/O performance. Again, the importance of this depends on your application. For a database like CockroachDB that is always reading and writing to persistent storage, this is critical. For other stateless applications, storage performance might not make as much of a difference. Now, there is a variety of different storage technologies available, ranging from classic spinning hard disks and modern SSDs to network attached storage and replicated storage. Even when running in the cloud, there are still a large number of choices that you can make when provisioning storage. Here, we're going to touch upon the top level experiments that you might want to run when benchmarking storage. And luckily, these metrics that we hope to gather are fairly agnostic to the storage technology we're measuring, other than that we'll get different results depending on that technology. And as with network benchmarking, storage benchmarking is broken up into throughput measurements and latency measurements. These measurements take on a similar meaning in the context of storage, but there are a few small subtle differences here. For instance, we're no longer dealing with symmetrical components. So latency is always implicitly defined as round trip latency from a user application to a storage device and back. Storage I/O measurements also have another dimension to them that is critical to acknowledge. Storage devices provide interfaces to read data and to write data. And these two operations typically have vastly different performance characteristics. We're going to want to measure both of these operations independently to paint a full picture of storage performance. As we've discussed a few times already, the first step to benchmarking, after determining what we want to measure, of course, is picking a tool to perform these measurements. Here, we're going to go with Sysbench, which you might remember that we mentioned earlier. Sysbench is an open source benchmarking tool that can be scripted at will using Lua scripts. The tool is popular in the database world because it began life as a database-specific benchmark. However, it has since generalized into an all-purpose benchmarking tool that provides for a lot of flexibility. For our purpose here, we'll be using it as a file system level benchmark as we test storage devices. Here's an example from our report about measuring the throughput of read operations using Sysbench. There are a few interesting things to note here that didn't come up in our previous micro benchmarking attempts. First, we can see that at its core, the benchmark is measuring how much data Sysbench can read from storage per second. We ran the benchmark over a range of concurrency levels, starting at 1 thread, reading alone, and moving our way up to 64 threads, reading concurrently. This is very interesting to test because different storage devices support different levels of concurrency. For instance, we can see that AWS takes an early lead, but plateaus around 8 threads running concurrently. Meanwhile, GCP starts slower, but hasn't reached its full concurrency limit by the time we hit 64 threads of concurrent readers. Finally, although not pictured here, we ran a few trials for each of these data points to improve the accuracy of our results. Similarly, we performed experiments using Sysbench to measure the latency to write 32 kilobyte blocks to storage. Again, we ran the benchmarks over a series of concurrency levels. And this time, the clouds scaled similarly to each other. We also measured the different types of latencies. We measured the average latency on both clouds and the 95th percentile latency on both clouds. These are both useful metrics to understand because they will impact your application's average and tail latencies respectively. In this case, we can see that AWS has a much tighter spread on their tail latency than GCP does. So the first tip we'll give is that Sysbench makes a distinction between sequential and random access reads and writes. This is important to consider when benchmarking because different storage technologies offer different performance characteristics between these access patterns. For instance, spinning disks perform much better with sequential access than with random access operations. On SSDs, the difference is less pronounced. The next tip is to determine, based on your application, how frequently you will want to perform syncs while writing. This is highly workload dependent and is a function of the guarantees you need out of your storage system. Because CockroachDB is a database that is constantly flushing its wall to provide durability, we decided to test with fsyncs after every write. We also set the fsync mode to fdatasync because that's the actual system call that we use internally. But this will vary depending on your application and depending on what you care about. The final gotcha is about benchmarking and more generally running on top of cloud-based persistent storage, or EBS for people familiar with AWS. When using this form of storage, it's critical that you think about the volume types beforehand because these can have a tremendous effect on performance. We'll touch a little later upon the differences we saw between Amazon's two SSD-backed EBS volumes, GP2 and IO1. So with that, I'll hand it back to Andy.
Great. Thank you, Nathan. The last benchmark that we want to talk about is TPC-C. And so I'll cover that here in this process. The previous three that Nathan discussed were sort of micro benchmarks, and TPC-C is a sort of application level benchmark. It simulates a online e-commerce platform with a number of different warehouses with multiple different transactions occurring at the same time. Using TPC-C, which by the way, there's a great TPC-C organization that explains the benchmark in more detail. We also have blog posts on our website that explain exactly how it works in more detail and all of the different components. We tested a number of different storage types, including SSD and EBS, to see what the differences in performance actually were depending upon these different machine types. TPC-C is measured in two different ways. One is this throughput metric called TPM-C, which is throughput per minute type C. And the other is number of warehouses supported. And so each warehouse has a maximum amount of TPM-C that it's allowed. And so what this allows you to do is in the benchmark, it actually takes both throughput and latency into account. In order to achieve top throughput, you also have to measure and maintain your latency as well. And so what this chart in front of us shows is a couple of different things. First, in the blue, it shows GCP's N1 standard 16 performance as sort of the benchmark comparison for the three different EBS types. We're in gold here looking at the C5 series. So again, this is the compute optimized series from AWS. It's the most recent one denoted by the 5. And then we're looking at the SSD, the EBS IO1, and the EBS GP2. As I mentioned earlier with the Amazon machine type names, you can actually infer what machine type it is by looking at it. So if you see the C5D.4x large here, that denotes the SSD, whereas the C5.4x large are the EBS types. Now, unfortunately, you can't tell if it's an IO1 or GP2, but you can configure that within your AWS setup. And so what we saw here is that with both SSD and EBS, the IO1, Amazon really performed quite well in comparison to GCP. However, in the GP2 setup, it was actually a little bit worse performance than GCP. And so, this tells us a number of things, but one, that performance can vary across the SSD or EBS storage types. And two, that you need to test multiple ones to figure out exactly what performance you need to achieve. And then, obviously there's different price profiles for these performance as well. And so sort of the takeaway that we came to, or the conclusion after this was, well, if it's not, SSD or EBS as the distinction between performance, what might explain the performance difference between AWS and GCP on this benchmark? We attribute a lot of the performance improvements to AWS's Nitro System. Nitro System was introduced in the C5 and M5 series in 2018. And what you can see here is all of the gold instance types from AWS here, the C5D, M5D, C5.4, and M5.4 along the bottom, all have the Nitro System. And so all of the machine types that have that Nitro System either perform at the same level as the N1 standard 16 from GCP or better. And so, we're not going to dive in too much about what that Nitro System exactly is, but it's a really important point to highlight, which is that, AWS took a big investment in this system and put it in their newest generation of machine types. And it made a big difference on the TPC-C benchmark when comparing to GCP. So it's sort of a good example of how things change, because the machine types that don't have the Nitro System often can perform worse than GCP. So now I'm going to talk about what we learned from this exercise. The first thing that I want to highlight here, and I kind of touched on this with the Nitro System a few minutes ago, is that we've heard from a lot of folks, and especially this is true outside the cloud, that the conventional wisdom is that sort of hardware performance is plateauing. We've reached sort of the peak performance here. And what we found in the cloud is that this might actually not be true. Our findings suggest that in the cloud, there are still performance gains coming, and that there are performance differences based on machine type and based on all of the different underlying factors that go into that machine type. And so this is something that will mean that in the coming years, it's really important to be able to recognize that and to understand that if performance is the most important characteristic for your workload, that you should stay on top of this information moving forward. The second thing I want to talk about is that, as I hope you've inferred from the conversation today, is that benchmarking is complicated. Cloud benchmarking requires a continuous process to keep up with the investment. So, we invested a large amount of time in running this information in the latter half of 2018. Unfortunately, we can't be done with it and say that we understand what's going on and put it down and not pick it up for a few years. There's always going to be new investments, and it's always important that if you're sort of reaching for the most performance possible, that you stay on top of these new investments. The second thing I want to touch on here is both picking your instance type and processor type with care. So we talked about this a lot, but across the different cloud providers, you have to know about all the options available to you. You have to test all of the options available to you, because you might get very different results based on those options themselves. So we definitely recommend that you read about them and do your homework, and kind of you can infer different aspects of performance based on the profiles, but there's really no substitute for actually testing this information yourself. And then finally, I would say that the last thing we learned is that the tools make the benchmark. We are a big believer in open source technology because it gives people a chance to weigh in on the different choices made in the benchmarking tools. And it gives you a way to have a language that you can talk about this with other people. If we had chosen non-open source tools, it would be really hard for anybody else to verify results or to talk about the differences they see in performing their own tests. So this is something that we want to highlight, is that we have provided several tools that we found useful, and as we learn more from our community or from our further tests, we'll continue to share those tools with the community. But please share them back with us if there's other tools that you find useful that you think we should test with in the future. The final thing I want to touch on here is about avoiding vendor lock-in so that you can take advantage of the latest investment. if you had a sort of one contract with a particular cloud provider, and maybe it's the best cloud provider right now today, but if another cloud provider makes a large investment that improves performance, if you're locked in, you can't take advantage of that. And so, the cloud providers that provide these, they want to incentivize you to use their entire suite of products, and there's benefits to organizations from using an entire suite of product offerings. But it's important to keep in mind that the performance of these offerings is only true at a given point in time, and advantages can last a much shorter period of time than your long-term contract. So it's important that you sort of realize that trade-off that you might be making by sort of committing all in, and where possible, picking open source tools, cloud agnostic tools that allow you to actually port your workload to whatever is on the most recent cutting edge. So if you were to pick cloud agnostic technologies, then you can actually take advantage of the best investments from any of the cloud providers. And so that's something that we would definitely recommend to our customers and to other folks out there, is that as you're thinking about these different options, you really want to make sure that you're well positioned to take advantage of the changes, because we know that the cloud movement has not reached its peak yet. It hasn't plateaued, and there's going to be continual investments here in the coming weeks and coming years. So that's the last kind of main thing that we have to share about what we learned. I know that we have received a few questions here. Maria, maybe I'll kick it back to you to highlight what some of those might be.
Yeah, first of all, thank you so much, Andy and Nathan. This is really great stuff. And for those of you listening in, keep sending through your questions if you have any. We did have a few come in. So I think actually the first one, maybe I'll start with you, Nathan. We got this question here about, was there anything that surprised you when you did the test?
Yeah, thanks, Maria. So there were a number of surprises along the way. The biggest probably was the swing between the 2 years, the relative swing between AWS and GCP. But when talking about specific micro benchmarks, one of the biggest surprises was the difference between the two clouds in terms of write latency on local SSDs. So Andy, if you don't mind, we did have a slide about this, titled example write latency results. Do you mind going back to that?
Yeah, 1 second. This one?
Yeah, this one right here. So this one, right off the bat, it's very surprising. We see write latencies that are quadruple from one cloud to the other. And so this is one of the cases where we actually started to try and dig in. And what we found was that when we enabled the no barrier file system option on both clouds, the difference between them almost completely vanished. And for those unfamiliar, the no barrier file system option changes the durability of disk syncs. It controls whether or not the OS kernel will instruct block devices to flush their write back caches on various sync operations like fsync and fdata sync. Enabling it can offer superior performance, but it does put you in risk of data loss in the event of power failure if you don't have something like a battery-backed storage device. So we're trying to avoid speculating too much about why enabling it had such an effect on GCP, but very little on AWS, but we're very interested in learning more about this.
Cool, thank you. And Andy, maybe this one is for you. How do I determine pricing when performing these types of comparison?
Yeah, thanks, Maria. So both cloud providers are actually pretty good about publishing their pricing information on their websites. There are a few things to keep in mind. So I'll actually point, GCP has a really good pricing calculator where you can actually choose the machine type, you can choose the processor type, the number of nodes, and it'll take sort of the static page of posted prices and actually compute the price for you and allow you to make a comparison. So if you've run a number of different machine types and you know the performance, you can actually see the exact price that you would pay using that calculator and then make a comparison to the right ratio for you. On AWS, there's a little bit more complexity involved because in addition to the machine types available, which there are more machine types, depending upon what type you choose, you actually have more inputs into price as well. So on the EBS IO1 type devices, you actually have to pick the number of IOPS that you want to provision for these machine types. And so this can be a little hard because it's often unclear exactly how many IOPS you actually need. And so it's something that you have to test with at different IOP amounts and determine how that influences your workload's performance, because these are a primary consideration that impact your pricing as well. And so what I would recommend is, pick the machine types that, sort of have an intuition that makes sense for you, run them on a performance basis, and then you can actually consult those websites directly and get sort of the pricing for that and get a comparison between the two in order to make the right trade-off for yourself.
Nice. Andy, one more for you. When will you benchmark cloud providers again? And will you include Azure?
Yeah, that's a great question. So I touched on this a little bit at the very beginning, but we sort of had an opportunistic process in producing the 2018 cloud report, and it led us to test AWS and GCP as their, were kind of the two leading ones that we had worked most exclusively with. And what we realized is that we actually want to know, we're really curious about what this looks like on Azure and some of the other clouds that our customers are bringing towards us. And we simply just didn't have the bandwidth to run through this full battery of tests for the 2018 cloud report, but we absolutely want to include them for the next version of this. So I would expect that we'll do another version of the cloud report later in 2019. And we will definitely be looking to include Azure as well as other cloud providers. So if there's a specific cloud provider you're curious about and are interested in it, please reach out to us and share it with us. But we're definitely hoping to expand, the learnings that we had here and do this again in 2019.
Great. I think the last one is for you, Nathan. It's about TPC-C testing. The question is, which tools were used for TPC-C testing?
Yeah, that's a great question. So we've actually used two different benchmarks for TPC-C testing over the time. The first is a tool that we've built internally that is Postgres compatible, given that Cockroach itself is Postgres compatible. So we can actually run it against Postgres and Cockroach and compare. But it also fits into our testing workflow. It's run every night. And it's what we use generally to push TPC-C as far as it can go, because there are a few changes in there in terms of how we perform batching between operations that just complement Cockroach's underlying key value model. But the tool is compatible with Postgres. Additionally, we've used a tool out of Carnegie Mellon's database group called OLTP Bench, which is striving to perform kind of these types of benchmarks across a number of different databases. So that tool wasn't the results that we published, although those results are pretty similar. But in general, if you have a TPC-C benchmark that works with Postgres, it will also work with CockroachDB if you're planning on doing your own benchmarking of this certain benchmark.
Great. Thank you so much, Andy and Nathan. I think that was all the questions for today. I want to thank the two of you, but also really our audience. Thank you so much for showing up today. You guys really make this content come alive, and we love your questions. Now, Andy, if you mind just switching to the next slide, I just wanted to let you know that we are hosting our next webinar on March 7th. It's about how to migrate from MySQL to CockroachDB. You can find it on our website, but we'll also include a link to this in a follow-up email that we'll send out shortly with the recording. So yeah, if you look out for that, and then I hope we see you again live on air next time. Thank you so much.
Thanks, everybody.